Hello. 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 All right. Yeah, I guess gonna solve uh Kth smallest integer in a binary search tree.
Hey,
It's my first time talking again in New Year. So yeah.
one. And if
So I'm currently
n
at the
happens to
start.
be equal to k, that means the current node that we just processed is the value we're looking for. Because remember, we are looking for the kth smallest element. So if that's true, then we can just return current.value and we're done. We don't have to visit
So we're
any extra
checking if
elements. But
the
what
n
happens if
is we add the n every time we pop the stack, and each traversal inside the while loop, well, it's also while stacked. While there's a stack, it does this. It does this first. After doing that, you stack that pop and append it to cur. Then add again to n plus equals 1, so 1. Then we go back here. Means it still has a stack. It's because we put it in. Oh yeah, because we append stuff. Yeah, here it's confusing, but I know cur is equals to cur dot left. We're gonna check the leftmost first, so so we can count it properly via. So the trick here is to make create a stack that will it mimic some sort of algorithm uh that will make the stack somehow sorted, and and each time you pop it um each time you pop it on this out of the stack, we each time you pop it we add an n. So that means once we encounter that n is equals to k, which means we found now the the let's say k is 1. That's the least. That's the first least value, lowest value that we're looking in, the first smallest element in a binary search tree. We then find that value, just create that val, which came from the stack of that pop, which we popped from the stack, if you get what I mean. But yeah, it's definitely confusing. I watched the video. This part is this part, so each time I know you traverse it from the left, and if you encounter null, then you can pop pop the stack, and then go back from the beginning, look to the right. If the right has something in it, you append it. Then after appending it, you go again to the left. If it can go deeper, if it's null, you pop it again, go back, check the right. If it's empty, pop it again. Then you return to the one that called this one, the root of the tree, and go to the right now, if you get what I'm saying.
if this is not the case? Well, we just processed current, right? That means that we're allowed to now go to its right subtree. So we can actually update current now and set it to current dot right. And so what's going to happen now? Well, the loop is going to actually go back up if current dot right is non-null or the stack is non-null. Then we're going to start our loop. And for that node, we're going to keep going left as much as we can. Maybe it doesn't have a left subtree, so then this part is not going to execute, and then we're going to end
Yeah,
up just popping again from our
null.
stack. And conveniently for us in this problem, we're guaranteed to have at least k nodes in our tree, so this is actually always going to execute. We're not going to end up exiting this while loop. So we actually
Okay.
don't even need a return statement over here. And this actually is the entire code. Let me just run it for you to prove that it works. And as you can see, it's according to this, not pretty efficient, but I'm pretty sure if I ran it again, I would get a much more efficient time. But you can see this is the iterative solution. It's roughly the same time complexity as the recursive solution. And surprisingly, it's not that much code, right? Like you might
This is the
expect the
first
iterative
search.
solution to be more complex, but we're actually not doing anything fancy. We're just going as far left as we possibly can, adding the values to the stack, and then popping from the
Okay, so
right
this is
when we need
iterative
to.
and this one is
So I hope
recursive.
this was helpful.
That's
If
cool.
it was, please like and subscribe. It
And there's
supports the
more,
channel a lot, and
and
I'll
they're
hopefully
very
see you pretty
confusing.
soon.
Alright, so we'll try to solve it using the iterative depth first search, I guess. So we first start with a stack to list, and then I'm right. We then create we apply the current node should be the root, so we start at the root. And I forgot the other one. If I'm right, it's uh yeah, that's excuse. Oh my god. Alright.
I'll go to it.
There, why is there n equals 0? Oh, this one's different. So this one uses given k and now checks. It skipped it. It's basically minus it again. I like that, I guess. But let's do the one that how it he solved it in the video. So equals 0. Now inside of the tree, while per and stack is still not non-null. I don't know how it ends up stopping because the stack is empty. But I guess it's gonna start. It's gonna automatically still gonna work, I guess. And inside of this, while per, we then check if we then check if what's that? Mm, I think we first start by appending it to the stack that append per dot file or no dot stack that append um per dot file says here stack that append per. Right, just not stop peeking at the solution. That's just a small hint. So we stack that we append the current, but why not the current that file? Actually, I guess we don't really need to append it at the value. I guess that's fine. You can just it's not the answer, I guess. Then per equals to per dot left. So now we check at the left point now. Man, it's really hard to think about this. And I already forgot, but that's okay. So we now check it at the per dot left. So now let's check it again. Oh, I forgot the pop. That's so confusing. No, check. So after going to the left, we now get the new current after the cause stack dot pop. Current equals stack dot pop. Yeah, just pop the just pop the one that we appended in the cur. So we just pop it, pop this one. No, no, wait. Well, this happens only if this happens only once that current now ends up in null. Once it ends up in null, we start popping it and getting back the numbers. So n plus equals 1. After this, we now then check if n is equals to k. That means we found the again the kth smallest integer, or the rank smallest integer based on k. We now found it. That means we can now go to the right. So that means cur is equals to cur dot right. And after that, we mm, after going to the right, then we can stack that, append the no. We can now get the value though. Yeah, we can just return it. So if k is if n is equals to k, what's how do we see?
Non-null or the stack.
Yeah, just return the value. I thought you had to pay. So if we then found it, the we just return the current, not the value, and you just go to the right, and that's it.
Looking for, because remember,
Actually,
we pretty
actually
efficient, but I'm
it's
pretty sure if
yeah,
I
yeah,
ran
yeah. It's current that value. If we're now at the specific node inside the tree that has this one, we're now good. We found it. Then we just go to the right again. And yeah, still really confusing. But I think, of course, each time it doesn't satisfy this, then we check the right one. So yeah, actually, this one is correct. This one is actually correct. So all right. So yeah, there's a wrong answer. I seem the output one now, but the expected return type is in. So oh well, stack or cur.
and maybe it doesn't have a left subtree, so then this part is not going to execute, and then we're going
But why though? Why doesn't this not work? Seems to be correct. Oh man, this
to. Okay,
should be
but
faster.
what happens is pretty efficient, but I'm pretty sure.
N equals zero stack one cursor. Correct. We we pop it correctly and put in cur. We add it correctly, and if n equals k. What? So while cur or stack then? That's the difference. I actually, yeah, because the stack is initially empty, of course. So it's not gonna happen. Yeah, I'm tripping. Anyways, thanks for watching. And today is January 9th, 2025, and thanks for watching again. I'm not sure if I'm even heard while I was speaking.